Hello, my name is Ethan Hunt, and today I'll be presenting my project on a first-come, first-served approach for the order of operations in arithmetic formalisms and programming languages. To start with, I would like to ask a question. What problems are solvable using the given programming language? And this question is very broad, and so I want to start with asking an easier question. And the best place to start, obviously, like I said, is to ask an easier question. And given the fact that one of the main things for Turing completeness is being able to handle all arithmetic expressions, I want to ask a question if a machine can express every standard algebraic equation. So, example right here is the Fourier series. And in order to do this, we're going to need to create a new formalism. What a formalism is a method of evaluating something. It's often a mathematical expression, sets of expressions, has basic assumptions and definitions. In this case, we're going to need two new definitions, preemptive and non-preemptive algebras. And we're going to need a new model of computation, the left-right temporary machine, and new classifications for expressions. Preemptive and non-preemptive algebras. Essentially, what this concept boils down to is that oftentimes in our normal arithmetic and algebraic equations, we follow PEMDAS. It's what most calculators would use, computers would use, and we often use parentheses to denote when we want to compute operations of normally like lower precedence first. So with multiplication being higher, we would often put parentheses around to like a plus operator on two numbers. So the idea is that what if a language didn't have that? Can it express every single expression in a preemptive algebra? What are the computational limits of this? And so, to answer that question, we're going to need to go over Theorem 1. And the first thing about Theorem 1 is essentially we can represent any language that's a preemptive language as a sequence of expressions. And the best way to think about this is that the sequence of expressions defines the order of operations that we must compute in. And we are just recursively tacking on and building up the expression from these basic parts. So we're going to like parse the expression and then compute it upwards. Kind of how a normal parsing does, but the important part of this is that we need to take the fact that we can express it as a sequence of expressions, and the final expression is equivalent to an S is equivalent to E. So what we're saying is that the final evaluation of these sub-expressions is going to be equivalent to the whole expression we're trying to NL. In order to answer the question I posed earlier about what are the limitations of non-preemptive languages versus preemptive languages, we're going to create a new type of model of computation. This is known as the left-right temporary expression machine. And this machine will compute a non-preemptive language expression, so we'll call it E, and this expression will correspond to a sequence of sub-expressions of some preemptive language. And the LRT machine will correctly compute the non-preemptive expression, and the output will correspond to what is expected from the preemptive language. One of the most important things that an LRT machine offers is its ability to encapsulate certain expressions and relate those expressions to finite memory. And what do I mean by this? So an LRT machine has two given registers. So that's the left and right registers. any operation must be computed between these two registers or on the register. So if it's a unary operation, it can be computed on L or R individually, or if it's a binary, it's got to be computed with both. Now, in order to handle order of operations like PEMDAS, a machine will need extra registers, aka temporary or auxiliary registers. And the number of auxiliary registers needed to compute an expression is the class of the expression. And we'll go over this in the future, but an LRT machine can have 1, 0, or n different extra temporary registers. The next important thing to note is that by Theorem 2, given a preemptive language L, every expression, E, that's an element of expressions in L, of class n, can be computed on a corresponding LRT machine with n auxiliary registers. So what does this mean? Well, an expression of class n, I had briefly touched on this earlier, and we will again later, is essentially the amount of memory needed in an LRT machine to compute it. And essentially what this says is that if we have a preemptive language, an expression that requires n auxiliary memory slots, then if there exists a LRT machine with n auxiliary registers that can compute it. To further explain the concept of classifying expressions, an expression in E, in a preemptive language, is said to be of class n if and only if there exists an LRT machine, M, with n temporary registers that compute this expression E using a finite set of expressions in a non-preemptive version of L. And essentially, that's just going back to Theorem 2, saying that if a expression requires a certain amount of memory, there exists an LRT machine that can compute it. And this, I give an example here of how, of a class 1 expression, which requires one temporary variable. So the idea of this is we've shown that there exist certain limitations in languages that, based inherently on memory required to compute something as a language. And this is going to be used to further build upon the idea of what problems are solvable in a given language. Thank you for listening to my project on the concept of using a first come, first served approach to arithmetic formalisms in programming languages.